Good morning and welcome to this, the first in the Physics 1900 to 1930 series. It's a 6-week series, and it's the first. It's a bit of an experiment for us here at the library. It's the first program we've done with Zoom, though not with YouTube. So just to remind you of upcoming series, there's one on the Nobel Prizes, which are awarded in October, and the series starts in November and runs, I think, the first 2 weeks in December, so it's a 6-week one. And the physics prize is the first, and then the chemistry, and then medicine, and physiology, and then I think the Peace Prize, and the economics prize, and then finally the literature prize. And the Belmay Elkins is doing the literature prize, and David Elkins the economics prize and the Peace Prize. So between the two of them, they're doing some of the most difficult parts of that program. So that's the Peace Prize. Then an innovative series that I've wanted to do for some time on how the brain works. And that'll be a 6-week series too. And that will run in January and halfway through February. And then a series on art and science with Penny Lynn Coulson, or Cookson, I should say. And Penny Lynn is an expert in the arts, gives many lectures, has a lot of experience, so that should be an interesting program. The InfoHealth series, which has been going on for 14 years here, hit a speed bump like so many other things did with the pandemic. And it's a program that heavily depends on direct interaction between the speakers and the audience, so we actually need a living, breathing audience for that program to work. So I'm not sure when that will start. I suppose it could start as early as January, but I doubt it. I would think the earliest will be, just my take on the pandemic, the earliest will be in September of next year. So that's what's coming. Well, then the next thing is why this series? It does seem a little odd to pick on the first 3 decades of the 1900s, but there's a reason for that. It was probably the most transformative and audacious period in science ever. And now that's saying something, because in the century before, we had Wallace and Darwin and their hypotheses with respect to evolution, which has really transformed so much. But still, I think this transformative period in physics in the first 3 decades is certainly a worthy equal or perhaps better. So one of the remarkable things about those first 3 decades was that it was largely a European venture. The number of people involved, I mean, the principles involved was never large. It was low budget stuff. And despite a very turbulent Europe and world, which I'll talk about in just a few minutes, they were very internationalist. They worked together very well, despite sometimes some very strong disagreements, particularly related to particle physics. But so it was quite remarkable with the political background of what happened in the first half of the 1900s. I mean, if you think back about it, World War I was quite enough disruption, but then the flu pandemic of 1918 through 20, the Great Depression in the 20s, and in the wake of World War I, 4 empires collapsed: the Austro-Hungarian, German, Russian, and the Ottoman Empire, and 2 were teetering, although they might have not known it at the time, and that would include the British Empire and the Japanese Empire. It was also a period in the late 1920s of the early movement towards fascism in Germany and Italy and Japan, and the parallel movement, the communist movement, primarily in Russia and China in its early days. So there was a lot going on in the background. Well, what about, why were these 3 decades so transformative? Well, think about it. There are 2 major areas that physicists transformed in those first 3 decades. First, to do with the universe itself. I mean, we started out, I'll get into this in a little more detail in a moment, but we started out with a universe that was essentially the Milky Way and not even all of that. And furthermore, that Milky Way was thought to be a relatively static affair with no beginning and no end. And by the end of those 3 decades, we knew that the universe had many more galaxies than just the Milky Way, and furthermore, it was expanding. And if expanding, there must have been a much smaller beginning. And that would be the beginning of the whole idea of the Big Bang. That in itself would justify a very remarkable 3 decades in astrophysics and astronomy. But you have to remember that in these early days, around 1900, there were very respectable people, physicists, who simply didn't believe the atom existed. Well, by the end of the 3 decades, we knew a lot about the atom. We knew a lot about the nucleus, primarily because of the work in Cambridge, and we knew a lot about the electrons and electron orbits, and what dictated those orbits, and how the atom worked. And we had working mathematical models that held up by the end of that 3 decades. So quantum physics went from 0 to mature within 3 decades. That was quite amazing. And if that were not enough, in the middle of all of this was Einstein's hypothesis related to time and mass, the whole business of relativity, and the realization that time was relative. It wasn't fixed in the Newtonian sense. And then, of course, Einstein, who was probably the most outstanding physicist of this period, he made his mistakes for sure, but I think most of his colleagues would acknowledge that he was probably the best of the lot. And he led the charge in the whole quantum hypothesis. Newton himself suggested that light might be made up of particles, but the subsequent evidence over most of the next 200 years was that it was primarily had waveform properties, and we'll talk about that in the series. But along came Einstein and Max Planck before him, 5 years before, and Planck reluctantly, Einstein not so reluctantly, provided the evidence that light and energy was quantized. It was particle-like, or at least could be particle-like some of the time. So that's and also there were, to just close out this introduction, by the end of that period, there were 4 well-established centers for physicists, and they were the biggest and the most successful were in Europe and Cambridge in the UK, Copenhagen in Denmark, and in Germany, Göttingen and Berlin. So let's begin. By the way, that first slide shows a magnificent picture of the Milky Way. just absolutely stuffed with stars. Now, I put this in because, just to add a little perspective, I mean, if we weren't humans, if we hadn't evolved as much as we have, I wouldn't be talking about this, you wouldn't be watching it, and we wouldn't be asking the kinds of questions that we're asking. So for life on Earth is probably from its very beginnings, maybe 4 billion years old, maybe a little longer than that. But it's only been in the last, say, for sure, 100,000 years, might be longer than that, our human ancestors would even think about questions, would look up at the sky perhaps and try to imagine what was going on and develop their own stories. This Australopith, anamensis, 3.8 million years ago would have had a brain, say, the size of a modern-day chimpanzee. It's very unlikely that this transitional form on its way to becoming human over the next several million years would have had the imagination to even begin to think about the kinds of things we're going to be talking about. So, and even if we look at, this is a skull from 320,000 years ago, one of several that were found in Morocco, and they were recently redated to this period about 325,000 years ago. They had a brain size, cranial size, the equal of ours. But if you look carefully at this CT scan of the skull, you can see the heavy brow ridges, the more prominent lower jaw, but maybe there was maybe such proto-humans were capable of imagining and wondering and looking up at the night skies. I don't know. The next two for sure, and it's interesting that the one on the right, these are both CT scans, and then the kind of endocast of the brain underneath it. Interestingly enough, Neanderthals had slightly larger brains on the average than modern humans, and at least the surface of the brain doesn't look a lot different between the two. Neanderthals, certainly there is evidence that they created art, and some of it certainly none as elaborate as was later developed in caves in Spain and France, but still, at least 100,000 years ago, maybe more for Neanderthals, and for modern humans, creating works of art at least 70,000 years ago, maybe a little longer. The point is that they were capable of imagining things. So maybe the beginnings of art and science, and I like to think of art and science as together. So what do art and science share in common? Well, they share evolutionary roots. The brain beneath the skull, I don't think the brain from a functional or physiological point of view differentiates too much between art and science. Those are somewhat arbitrary barriers that we create. Both require creativity and imagination, skill and training. They involve storytelling, and there's an element of beauty clearly in both. We don't often think of beauty in science, but probably more than any other discipline in science, physics, and certainly the mathematics, a sense of if things are elegant, if the solution is simple, if it's elegant, if it's straightforward, if it's obvious, if it's intuitively correct, or at least it makes sense intuitively, it's probably correct. So that's something we'll explore later. Now, I've already talked about the origins of art, earliest art. Interestingly enough, the cave art began more or less, well, I'm talking about cave art by modern humans, developed at about the same time period, say 40,000 years ago, or maybe a little bit more in Indonesia, but around the same time. And here's an example of one scene in Indonesia. This one's been, this one's probably about 44,000 years ago, but it's a hunting scene, and the human figures, you can see at the bottom left, on the left side and bottom left, human figures are so much smaller than the game. They're apparently hunting. But anyway, there's a story here. Now, some interesting quotes. Isaac Newton was the Einstein of his day. And these are two quite meaningful quotes to me anyway. And the first one, to explain all nature is too difficult for any one man, and even any one age. And I don't mean his particular age, whether he was kind of 50, 60, or 70, but an age, say a period. And then the second one, the scientist comes through. 'Tis much better to do a little with certainty and leave the rest to others that follow you, than to explain all things by conjecture without making sure of anything. I would certainly support that one. Now, this is a lovely one, because here's this enormously productive 3 decades. We're on the threshold of 1900. And there's Lord Kelvin, honored, justly honored, as a major figure in science in the UK. And he says something like this: there is nothing new to be discovered in physics today. Wow, what an embarrassment. Just 4 or 5 years later. The revered Lord Kelvin reportedly told the British Association for the Advancement of Science in 1900, all that remains is more and more precise measurement. Well, to me, these are like tales told by older men. But now a little more focus here. This sense that in ancient times, and right up to 1900, that the universe writ large had been like it wasn't changing very much. In a Newtonian sense, it certainly did. The planets got wet around the sun, or planets around whatever sun that they were revolving about. But other than that clockwork precision, it was pretty much a static affair. And so here we are, Aristotle. Throughout all past time, according to the record handed down from generation to generation, we find no trace of change, either in the whole of the outermost heaven or in any one of its proper parts. Wow. Oh, he was wrong, but we'll see. And Copernicus. The matter of state of immobility is regarded as more noble and godlike than that of change, i.e., for things not to change was the preference rather than change. Don't think I agree with that one. Well, here's a quote from William Shakespeare's Julius Caesar, who says, "But I am constant as the northern star, of whose true fixed and resting quality there is no fellow in the firmament." Well, I don't think Shakespeare was talking about astrophysics. Well, let's look at the preceding, the 1800s, the 100 years before this 30-year period. It was a pretty active period. Darwin and Wallace, they were both naturalists from the same country who came up with pretty much the same idea of evolution by natural selection, independently of one another. And when it came to it, their work was presented to the same society on the same day. Faraday and Maxwell, they provide a very sound framework for electromagnetism. But this was the period of the Industrial Revolution and the steam engine and the interest in thermodynamics, or the study of heat and energy. And it's the second law, and entropy, which is perhaps the more important one, because it states that that overall, statistically, overall, the direction which energy is taking in the universe is from accessible to inaccessible energy, or entropy, meaning that eventually, even though the overall energy available in the universe will be the same, less and less of it will be useful or accessible. And essentially, that puts a bookend on the end of the universe. So we'll talk about that later. Now, let's look at the universe in 1900. There was one galaxy, that was the Milky Way, and there simply weren't the tools to map the whole of the Milky Way at that time. It was thought of as stable, and none other than Copernicus, later Kepler and Newton, thought exactly the same, that the universe as they saw it had no beginning and no end. The Newtonian perspective on the universe was that time everywhere was the same and under all conditions. And of course, nothing had been described like black holes or gravitational waves. Energy was thought of as not particular, meaning made up of particles, but continuous. And that was quite consistent with the way Faraday and Maxwell described the electromagnetic spectrum, of which light, visible light, is a small part of that spectrum. So that was the universe in 1900. Now let's go shooting ahead to the end of this period. How had things changed? Well, for one, it was no longer a story of just one galaxy. At least 40 different galaxies had been described. Einstein's work on general relativity had been published in 1915, and several people, including this Friedman and Lemaitre, looking at his equations, suggested that the universe was expanding. And if you think about it, if the universe is expanding, then it must have been very much smaller at some earlier period, and that would lead to the hypothesis for the Big Bang. Now, one of the issues in the early part of these three decades was that it was very difficult to measure distances for astral bodies. I mean, it was fairly easy to measure distances, for example, to other planets and the sun, but anything much further out became problematic. Edwin Hubble made his contributions in 1924 and 1929, at least in that period here, and showed evidence, actually the first experimental evidence, that, and not on theoretical grounds, but experimental evidence, that in fact there were there was more than one galaxy, more than one Milky Way, and showed evidence, particularly toward the latter part of the studies, that those other galaxies were speeding away from one another, and the further out they were, the faster they were moving. There was no talk of black holes at that time, but I mentioned that here because Einstein's general relativity, which was published, I think, in 1916, but people were aware of it a year before that, actually predicts the possibility of black holes. So more about that later. Now, what about comparing 1930 with now? Well, in 1930, at the end of this golden period, the 3 decades, we had 40 plus galaxies. Now, estimates suggest there might be at least 2 trillion and more, possibly. In 1930, there was some conversation about other habitable planets, but just doing the math on the number of galaxies and the realization that on the average, galaxies contain around 100 billion stars, and many of them will have planets, and a goodly number of them might have the conditions for life. It becomes pretty obvious that the possibility of life developing, at least in some form, in many places, is very high. If you ask somebody about black holes in 1930, they might have answered what? Now it turns out that black holes are quite common, even though it was just last year where the first actual picture of a black hole was revealed. And dark energy and dark matter, these are entities that were described in the latter part of the 20th century. Dark energy is a force that expands the universe, and dark matter adds a gravitational force, and so is important in the formation of galaxies. So they were described. That's part of the lexicon of astrophysics these days. Space telescopes, none of them in 1930. Now there are a lot of them. So, big changes. Well, what about the matter of measuring distances to stars in the early 20th century? Well, I suppose the simplest way to do it is use trigonometry. If you have 2 points on the surface of the Earth and measure the angle subtended by whatever you're looking at, a planet or a star, from both vantage points, and you know the distance between those 2 points on the surface of the Earth, then it's really pretty simple trigonometry to figure out, or at least estimate, what the distance to that astral body must be. The trouble is that only works for planets within our solar system and maybe some stars that are near neighbors of ours in the Milky Way, but not much beyond that. Another way to do it is to look at the brightness of stars. Now, just imagine if you had a friend and he had a flashlight beside you and you asked him to shine it on you and then back up. Of course, the flashlight will get smaller and smaller, but also the light gets dimmer and dimmer and dimmer. And so the light at the source of the flashlight might be thought of as the intrinsic light, what that flashlight is actually capable of generating, very close to the flashlight. But if my friend backs up 100 feet, then I'm looking at an apparent luminosity or brightness diminished by distance. So here's the hint about a way to measure distance to stars. So here's just going back to that trigonometry business, you could expand that a little bit by simply taking advantage of the fact that the Earth circles the sun once a year. And if at the 6 month marks, the 2 6 month marks, you take a line of sight on a star, you have a subtended angle, and you can figure out, again, using pretty basic trigonometry, an estimate. You can estimate the distance to that star. So it expands it a little bit, but not much further within the Milky Way. Now, this Henrietta Leavitt is the person who really broke this open. She was born in 1868 and died of stomach cancer in 1922. And she's very important because she provided us with a roadmap, a way to measure the distances to faraway stars, including some of these nebula or galaxies that were described by Hubble back in the early 1920s. So she's a very key figure. Now here's an interesting, I put these two photographs together because it's the same picture I just showed you of Henrietta Leavitt. Here's another young lady doing undergraduate work, and but using some of the tools, more sophisticated, I might add, than Henrietta had any access to, but they have a similar interest in measuring the distance to stars. So Henrietta Leavitt and Kate Hartman. Now, Henrietta Leavitt was one of these computer women at the Harvard College Observatory. Now, we're talking about the period in the say very early 1900s, and women were employed to do the calculations, to analyze these photographic plates and measure things and do the math. What Pickering, who is the boss here, considered work for women. Anyway, there they are, the 12, well, there are two men on the right-hand side, but the other computer women. Women really hadn't made much of a dent in science in any discipline around this time period. And before that, I just mentioned two of them here. Maria Mitchell, who died in 1880. She was the first recognized female scientist in the United States. And Sarah Whitting established a physical laboratory at Wellesley College in Boston. But there weren't many. But the landscape was changing, even if grudgingly and slowly. Here's a list of women's colleges in Boston. And the first one, the Vassar in 1861, and Radcliffe, which Henrietta, its predecessor, many decades before, Henrietta Leavitt went to and got a degree from. And so here it is. She attended Oberlin College, and then transferred to Harvard University Society for the Collegiate Instruction for Women. This was later Radcliffe. And she did receive a bachelor's degree in 1892. And then in the fourth year, she took a course in astronomy, and she really liked this astronomy, and began working as one of these computer women at the Harvard College Observatory. She was hired by this interesting fellow, Edward Charles Pickering, to measure and catalog the brightness of stars. Now, she was given the job of mapping the locations and the brightness or luminosities, as well as the periodicities of species of stars called variable stars, Cepheids. And variable stars are stars that expand and contract on a regular cyclical basis, sometimes over a few days, sometimes over a few weeks. The longer the cycle period, the brighter these stars. And these are quite large stars. These are much larger than our sun. So they're very good beacons in the cosmos. So she did a landmark study, and the title of the study was Periods of 25 Variable Stars in the Small Magellan Cloud. She did all the work for this. It wasn't Pickering. But the only acknowledgement of Pickering was this one sentence here. The following statement regarding the periods of 25 variable stars in the Small Magellan Cloud has been prepared by Miss Leavitt. That's it for acknowledgement. That was a major study on her part. That was very important. Now, the crux here was that she was able to show, in fact, I'll just go on to the, yeah, here's one of these variable stars. You can see it contracting and expanding. That expansion is apparently related to how much ionized helium there is in the atmosphere or the outer layers of these stars. And here are two examples, and I included really a figure from one of her studies. And on the bottom scale here, at least on the left-hand side, it's 0 to 30 days, and then on the right-hand side, 0 to 10 days. But so two different stars, and you can see the variation, the swing in the brightness or luminosity of these stars. And here would be kind of a 2020 version of this, cleaned up, for a star that has a relatively short period, 5.4 days, but some of them can be up to several weeks. And the apparent brightness of the star changing in a cyclical pattern. And if you do log plots of these, it's pretty obvious that the longer the period of the star, the brighter the star. So, but I think I've already told you that. Now, the evidence that she provided, I mean, what Henrietta Leavitt provided was a detailed account of these variable stars, these Cepheid stars, and showed that there was a very clear relationship between the period of the star, the cycle period of the star, and the brightness and or luminosity of the star. That in itself is not enough to tell you what the distance is to that star. The missing piece in the puzzle was provided by Hertzsprung, who examined a group of these variable stars that were much closer to Earth, which allowed him to actually measure the distance to these variable stars accurately. Well, now we had, with combining her work and his work, we now had a way to measure the distance to the stars, because we had a way to establish the relationship between what the brightness of the star is, the intrinsic brightness of the star was, to the cycle period of the star. So if you knew the cycle period of the star, you now knew what the intrinsic brightness of the star was, and the only other missing piece of evidence you needed was the relative luminosity as measured on Earth. It's very easy to measure the distance then to that variable star. So it was a major breakthrough, and even if her work wasn't acknowledged the way it should have been by her boss and others in the United States. It's very interesting that in 1925, a professor, Midge Leffler, of the Swedish Academy of Sciences, wrote to Henrietta Leavitt to inform her that he wished to nominate her for a Nobel Prize, and was surprised to find out that she had been dead for 3 years. They don't award Nobel Prizes posthumously, unfortunately. That was too bad, but the work was very important because she provided a way for measuring distances to faraway objects in the universe, such as other galaxies. That was very, very important. Now, since then, other standard candles have been used. There are even larger, bright stars. But perhaps one of the best standard candle are supernovas. Sometimes, or not sometimes, but often stars, when they burned up much of their energy, collapse in on themselves and explode and create a very bright object in the universe that can be seen enormous distances and far further out than variable stars, for example. And so here's another excellent standard candle with which to measure distance in the universe. And here are 4 examples of galaxies. They all look quite different, but that's what these supernova can look like. These explosions, if you like, they don't last long. I mean, it's a matter of days, maybe even a week or so. But they are, and next week I'll deal with this, but they are the birthing place for most of the elements in the periodic table. So as much as it's a destructive event in a way, the final stage for many large and medium-sized stars in their life, it's the source of the elements for the periodic table, including the elements that form the basis of life. So without these supernova events, we would not be here, or any life, period. Now here's an example. Now this is speeded up greatly, but it shows an explosion or a supernova. It's really quite a dramatic picture. Now, here's, you can tell from the palm trees here that this must have been taken somewhere around the tropics or near tropics. It's probably Hawaii, so maybe some distance from the tropics. But anyway, on a black night, the canopy above it can be just stunning. And Alan Lightman, who is a physicist and author, and had the unique position for a while at the Massachusetts Institute of Technology in Boston, the unique position of bridging the arts and the sciences. So he taught physics, I think, I'm making this up, but taught physics for half the time and arts the other half the time. I don't know what the actual relative distribution was, but in one of his books, he begins with this image in a boat, pitch dark, and a bright night, no clouds, and no human lights distorting things, and looking up at a sky like this. It's stunning, isn't it? Now, I think you know, perspective is very important, and one author I do like is Michael Shermer, and this is from a book he wrote, Why Darwin Matters. So I'll just read this little piece to you because it's a way of, there are 2 of these perspective pieces, but to read this, what science tells us is that we are but one of hundreds of millions of species that evolved over the course of 4 billion years on a tiny planet among many, orbiting an ordinary star, itself one of possibly billions of solar systems in an ordinary galaxy that contains hundreds of billions of stars, itself located in a cluster of galaxies, not so different from trillions of other galaxies in an expanding universe that is very possibly only one of a near infinite number of universes. Wow. If you want perspective, that's perspective. That's really quite extraordinary. He has another piece that I quite like. Remember when I started out this talk, I showed an Australopith, and here's the story that Michael Sherman, I'm paraphrasing here, but he tells. He's an amateur astronomer, and he was looking at Andromeda, the nearest galaxy to Earth, and the Milky Way one night, and thought about it, and realized that the light that was falling on his retina, his eyes, began its voyage from Andromeda 3.2 million years ago, about the time that the iconic, famous Lucy walked the Earth. That's an extraordinary thing, but it's a reminder that the distances are so enormous in space that to look far out is to look far back. I think that's a very important one, and I just wanted to end on one piece here that it's lovely. I'm a fan of Billy Collins. Billy Collins was a poet laureate of the United States for several years, and he wrote this lovely one on the first geniuses. And so it's, well, see what you think. It is so early, almost nothing has happened. Agriculture, an unplanted seed. Music and the felt hat, thousands of years away. The sail and the astrolabe, not even specks on the horizon. The window and scissors, inconceivable. But even now, before the orchestra of history has had time to warm up, the first geniuses have found one another and gathered into a thoughtful group. Gaunt, tall and bearded as you might expect, they stand outlined against a landscape of smoking volcanoes, or move along the shores of lakes, still leaden and unnamed, or sit on high bare cliffs, looking like early arrivals at a party the Earth is about to throw, now that the dinosaurs have finally cleared the room. They have yet to discover fire, much less invent the wheel. So they wander a world mostly dark and motionless, wondering what to do with their wisdom. Once in a while, someone will make a pronouncement about the movement of the stars, the density of silence, or the strange behavior of water in winter. But there is no alphabet, not a drop of ink on earth. So the words disappear into the deep green forests like flocks of small, startled birds. Eventually, one of them will come up with a compass or draw the first number in sand with a stick. And he will let out a shout like Archimedes in his tub, and curious animals will look up from their grazing. Later, the water screw and the catapult will appear, the nail, the speedometer, the bow tie will follow. But until then, they can only pace the world gravely, knowing nothing but the thrumming of their minds, not the whereabouts of north or the notion of zero, not even how to sharpen a stone to a deadly point. It's a lovely piece. It's humorous, it's fun, but there's some truth in that. So next week, we move on to the second part of this 6-part series, and it's about the expansion of the universe and the Big Bang, and about the creation of the elements of the periodic table, and especially the elements that relate to life. So that's the job of next week. And then we change gears a bit, and we talk about, we're going to talk about the quantum. And so that's the program for the next 2 weeks. I hope you're enjoying this as much as I am. It's been a pleasure putting it together. So thank you very much. Look forward to seeing you in a week. Bye-bye.